Okay, so let's continue on with now electric fields with multiple points. The PowerPoint is going to look a little bit different than what your notes look like. So just let me know if there's a part that isn't the same so I can adjust with it, because they'll be slightly different. So we just talked about this not too long ago. Let's look at some charges here. So does it start with drawing the two circles in your set of notes? Perfect. Two positive charges. So if you remember from the last lesson, what do the lines look like around positive charges? Yeah, exactly like that. So they don't, if we put a test charge somewhere, it's going to be repelled by these two objects. So if I put a test point over here, this is pretty straightforward. It's going to push it this way. If I put a test charge over here, it's going to push this way, push this way. If I look on this side, it's going to look like this. But once we get closer to the other test charge, so imagine I put a point charge here. So it's going to be repelled by this one, but at the same time, it's also going to be repelled by this one. Not as harshly, but it's still going to be pushed by that as well. So it's now looking at what is the interaction between these two charges going to do to my point charges. So if I have a charge here, it's going to go up, but it's going to bend a little bit this way. Same thing over here. It's going to bend a little bit like this. Same thing with this. It's not going to go straight out like this. That would be if it was just a single point charge. Now it's going to have a bit of a curve. Same thing here. So this pushes a little bit out. And if I put something in the very center here, it's going to be at a very unstable equilibrium point. Normally we don't really consider something in there. But you're going to have stuff like this. So they are going to basically push against each other. And here's where you can get some really fun symmetrical art pictures of drawings like this. Where you can see here, you can almost imagine like these are fingers that are pushing out in this direction. You can almost see the repulsion. They're pushing against each other and they're causing this kind of divergent to occur. So these two are repulsing each other, they're repelling, and they're pushing away. Questions with that? So what do you think it's going to look like if these are negative charges?
The test charge is positive.
The exact same?
No.
What's going to change?
They're going to point to the circle, it's going to be the same thing.
Okay, so let's imagine what would it look like with negative charges. Same thing, except instead of going away, it's going to go towards. And I'm too lazy to draw this out again, so we're going to do it like this. So same thing, just now all your arrows are pointing inwards. It's not as easy to see how these two are also repelling, but they are. There is another space to do two negative charges, right? On your notes? Okay, good. I'm not just doing this out of nowhere. So those ones look very similar. Yep, good. Now let's try opposite charges. So let's say that this one is positive, this one is negative. And let's see what this looks like. So positive charges, that's going to have a repulsion. So it's going to have electric fields that point like this. Negative going to attract a positive. So it'll look like this. What's going to be the interaction in between them? Arrows pointing towards each other? No. Because then it would look like the charges we just looked at. Yeah, so imagine I've got a positive point charge here. What is this charge doing to my positive charge? Repelling. It's pushing it to the right. What is this charge doing to a positive charge? Attracting. So both of these objects are working together, and it's going to push in this direction. If I put something here, it's going to be repelled a little bit upwards, but then it's going to be attracted down to this one. So we get this nice little bendy effect going on here. That looks like this. And technically, this one is going to loop all the way down, make a big, huge loop around, and come back here. So this is your interaction between a positive and a negative charge. Repelled by one, attracted to the other. What is this? So as these two fields interact, in this one they're working together. Are there spaces to write these on the notes? Yeah, okay. Did you get the one from the last slide, or did I go too quick? I can go back. So in this one, the two electric fields work together. In the last one, they're working against each other. Determine the electric field. So here, note that the electric lines of force work against each other. And I think this is one of your spaces too. So electric fields are vectors, so we add them as vectors. So you can almost picture it if I were to let's say take a specific point. So let's say I picked this point here. If I wanted to know what's the total electric field at that point, I need to add the electric field from this charge and the electric field from the other charge. So from this one, I'm going to have an electric field pointing this direction due to this. From this one, I'm going to have an electric field that's pointing like this. And if I add those two together, this one plus this one, it's going to give me an overall pointing to the right, which is exactly what this line is doing. At this point, I've got an electric field pointing this direction. I can do that at any point on here, and you'll get that same thing. So just as an aside, that's how they got those, is you're just simply adding those vectors onto there.
I'm not looking for the line.
So this would be the total, is the horizontal one. If I take this vector plus this one, it'll add up to that horizontal that we get at this point. So let's try some examples. So what is the electric field midway between two charges that are this far apart? So like I said, with electric fields, if I want to know the electric field due to multiple items, I need to add them like vectors. Here's where our vector unit comes into play. So here's what our situation looks like. I've got a 2 microcoulomb charge over here. I've got a negative 4 microcoulomb charge over here. They are 0.6 meters apart. I want to know what is the charge at point P here in the middle that's halfway between them. So 0.3 meters to both sides. So if I want to figure out the total, find the electric field due to each charge and add them together. So we need to also take into account the direction, but we're not putting in negative signs. So let's see how this works. So to figure out electric field 1, so that's from the charge on the left. So what is the electric field due to this one? Well, just KQ1 over R squared. Get a number.
Is this the electric field that the test object would experience?
Yes.
Or just the electric field that this object may observe?
Same thing, yeah. So we're saying, imagine there's a test charge here. There, it doesn't really matter. What's the electric field at this point because of this? It's going to be this one. Then what's the electric field at this point due to this? Which is going to be this. So I've got my two electric fields, but now I need to take into consideration direction. So notice I didn't put negative charges here, but I need to look at what direction do these fields point. So we're not putting a negative in here. We're taking that into account right now. So same thing with forces. When you drawed free body diagrams and you did forces, you never got out a negative force. We just considered the negative when we looked at what direction are they pointing. So if I look at electric field 1, due to the positive 2 microcoulombs, what direction is that field pointing? So if I were to draw an arrow at this point, where would E1 point? To the right. So my E1 is pointing this way. How about E2? Same direction, because this one's negative, right? So because it is negative, my positive charge here is going to be pushing this way. So they're both going in the same direction. So there's where the negative comes into play. The negative tells me, do I add these? Do I subtract them? What do I do? So in this case, I'm going to add them together. Pardon me? No, these are static. Nope, they're not moving. They're not moving. So this unit's called electrostatics, meaning we're going to keep them static. They're not going to move. So you're right in the fact that if I were to let go of these two objects, they're going to come together. That part's right, but we're not saying what happens when I let these go at this point. We're just looking at what's the field strength at this. Yeah, we're just going to imagine we're just taking a snapshot of this situation, just figuring this out. So like I said, in this case, we add them, and this is your total electric field strength. And this makes sense, right? This is exactly what we looked at in the picture between a negative charge and a positive charge. In the middle, there should be an electric field strength pointing this way. We just calculated that in the middle. So it just reinforces what I just showed you in the previous picture. Any other questions with this?
If we're looking at this from the perspective of testing, wouldn't the electric field change because we're going to have different Q values with the same R value and K value?
So you mean if I put a test charge here, will this change?
No, like if I was solving for the electric field, but I was using like the charge of the test object.
Yes. So if I was using the charge of the test object instead of these ones, yes, it would change. But we're not looking at the field strength of From this object's of this object, we're looking at the field strength of this and this. So same thing. If we looked at gravity, imagine there's an astronaut floating above the Earth. If we wanted to know what's the gravitational field strength at that point, it doesn't matter if it's an astronaut, a satellite, the moon. We just care what would be the acceleration at that point. So let's try another one. I've got two charges. We know the distance apart. We want to know what is the field strength between them. And now we're not exactly in the center. So we're going to be 0.1 meters from the first charge and 0.3 from the second. So here's our situation. The charges are the same. We now have a different point. It's more slightly to the left. Again, if I'm looking for the total electric fields, find the electric field of each of the individuals and either add them or subtract them, depending on the direction of the field strengths. So we'll solve for E1. This is going to be due to the left-hand charge. So we've got K, we've got Q, we've got the distance between them. We get a number. Do the same thing for the other charge. So the only thing that's going to be different is the distance between them. Now it's 0.3 instead of 0.1. So the question then becomes, do we add these or do we subtract these? Subtract them, how come?
Because this object, this charge is repelling it, and this charge is not repelling it.
Yeah, so both of these objects are going to repel. So if this is my first object, I've got E1 is pointing this way. E2 is pointing the other direction, but it's smaller, as we just calculated. So therefore, in order to figure out the total, it's kind of like doing the winning force minus the losing force. Except now it's the winning electric field minus the losing electric field. So bigger minus smaller. So yes, now we're subtracting. Opposite direction, so subtraction. For these questions, again, I'm not expecting a direction for this. You don't need to do that. I will be able to tell based on what you've done here whether you know which one's bigger and which one's smaller. So don't worry so much about that. I'll be able to figure it out. Questions with this? These are all in a straight line. We are not in a one-dimensional world. We are in a two-dimensional, well, three-dimensional. Unless you consider time as a fourth dimension. So, same thing. What's the magnitude? Now we need to include direction of the electric field due to these 2 points. This is nothing new. This really isn't. If I said, this is a force pushing this way, this is a force pushing this way, what's the total force? If I said, this has a momentum this way, this has a momentum this way, what's the total momentum? If I said, what's another case I could do this? If I have a tension pulling this way, a tension pulling this way, what's the total tension? Your method for solving this is the exact same as everything you've seen. This is really nothing new, except the equations are slightly changing. But if I want to know the total electric field, calculate the two electric fields, add them like vectors. So now we've got angles thrown in there and triangles, but really very similar to what you've seen before. Your strategy for solving this is basically the same.
I have a question. So we're saying that if you have a negative thing,
Charge?
then that and we have a positive thing, then the repel is right.
So Positive will attract or repel and negative will attract in these cases because we're saying our test charge is positive. We're not saying that negative always attracts and positive always repels.
That was leading to my question.
Okay.
Why are we always assuming that this is positive?
Because that's what they decided when they set the directions for the electric field. They just said, let's assume it's a positive test charge.
So will I ever encounter a question where a negative repels?
Yeah,
Like,
when you have another negative charge.
no, I'm saying, will that,
With electric fields, you mean?
yeah,
No.
will the test charge ever be negative?
Test charge is never negative. Do you remember do you remember last year when we did circuits and we talked about the current and what direction the current flows? And we said back in the day, scientists chose that positive charges were what moved through the circuit when they realized it was actually the electrons that moved. Similar thing. They picked positive charges to do for this because that was the convention. So they could have done negative charges and done the whole thing that way, but just conventionally that's what it is. I mean, technically the whole thing of positive and negative charges could have been flipped. Electrons could have been negative, protons could have been, electrons could have been positive, protons could have been negative. It's just how it was picked. Okay. So let's calculate these. So if this is my point here, we call this point P, it doesn't really matter. First thing we need to do is figure out what is the electric field due to our two charges. So electric field 1 from our 12 microcoulomb charge, again, KQ1 over R1 squared. I've got the charge of that electron, or sorry, not electron, the charge of that object, the distance between them, can calculate that. Do the same thing for our other charge. We've got Q2 is going to be 8 microcoulombs. Again, there is no negative that we put into this. We've got a different electric field. And then in order to figure out the direction for this, or what happens, let's draw some electric field lines. So at point P, what direction is E1 going to point? The first electric field, where's that going to point? So this one is positive. We're imagining there's a positive charge here. So E1 is going to point down. How about E2? To the right. Negative. It's going to attract this one. So from this, we've got two vectors. We've got what the value of each of those vectors are. Let's add them like vectors. So here is adding these two things like vectors. We just need to solve for what's the total, get an angle. This you should be able to do pretty easily, Pythagoras, and using tangent to get the angle. So I'm going to judge it based on how you created your situation. If you did it like this, I can see that you're solving for this theta. If you decided to create your triangle like this, then I would mark this theta as correct. It always needs to be from where your total starts. Yeah. So if this would be 50, then if you went about and solved this, this would be 40. So I would accept either one of those as correct, depending on which situation you set up. So that's why it's really good for you to draw out these diagrams. Yeah?
Why is I ignore the diagram where the E1 is going upwards and downwards? Like I ignore the diagram?
Which diagram do you mean?
The E1 is going downwards.
Mm-hmm.
Not in that.
So that's because so this is a positive charge, right? And at this point, we're imagining a positive charge. So it should be pointing down. Yeah, so here's where the test charge is. This is the point where we're looking at what's the electric field at. So I think, if I remember correctly, this is the last thing in your notes. Yeah. So you can imagine with this, this doesn't always have to be 90 degrees. So I could add to this. Yeah, just here is good. Thank you. So you can imagine with this, I can ask for something that's not. Actually, is there something that's not at 90 degrees? Yeah, I could give you something that's not at 90 degrees. It makes it a little bit more complicated, but I could. Typically with this, you would see more 90 degrees, I think, for this one.
And how will you solve it?
Sine law, cosine law.
Or the other
Or component method, yeah. Those are a little bit trickier. That's why I'm trying to think. If I look at the notes, I don't think I give you anything for this that is not 90 degrees. No, I think everything I give you is 90 degrees. Okay, so that is the second lesson.